All right, let's get started. The inverses. So inverse is simply when you're switching input and output. That's all it ever is. The input and output switch. But you do have to have a very strong understanding of it because you are going to have to deal with some pretty complex calculus stuff that deals with inverses. So as you imagine, the domain range would also switch when you have inverses. So that's kind of the big one. The domain and range also switch. Let me do these 4 possibilities here, and then I'll give you guys kind of a more concrete example. So a relation that's not a function has an inverse that is a function. Okay, so when you're not a function, what rule do you fail? Exactly. So if your relation is not a function, it could look like this. I'll just do like a sideways parabola. Okay, so that's not a function because clearly that fails the vertical line test, right? But would its inverse be a function? It would. So how would the inverse of that look? Actually, let me redraw that more time. I'm not going to make a big change. I'm just going to draw it like this. Anyone know what equation that would be? It would, totally. So its inverse would be what then? Y equals x squared. So that's an example where the relation is not a function, the original is not a function, but the inverse is. Okay. Now let's do the other way around. A relation that is a function, but its inverse is not. So you just reverse it, right? So in this case, I could do something like this here. Y equals x squared. And then, of course, x equals y squared. By the way, let's look over here again. On blue. What's the domain? This one here. No, what's the range? But then, what's the domain here? The polyreal, and then the range will be from 0 to 1. So you see how this works. Now, let's do something where both the regular and the inverse are not functions. Yeah, anyone have an idea? Totally good. Yeah. Yep. Okay, that's a crappy looking circle. Maybe an ellipse, whatever. But yeah, both like x squared plus y squared equals 1. That's a relationship. More specifically, this relationship is circular. But the thing is that if you try isolating y, you can have y equals plus or minus. If you try isolating, you have this y equals plus or minus root 1 minus x squared. Because that plus or minus situation, that's why you have more than one output, right? And because of the x squared, you can plug in like 1/2 and negative 1/2. You still get the same situation. So, and then obviously this one should be pretty easy. What equation would you say this is like? Y equals? Yeah. So in this case, it passes the vertical line test. Both cases. The inverse would be y equals a cube root of x. You did the inverse, which looks like this. Both pass the vertical line test. So, yeah. And by the way, going back to the circle, the inverse is the original. They're the same thing. Okay. So those are like the 4 possibilities. And again, domain and range do switch. Like for y equals x squared, x equals y squared, we saw that happening. Domain and range do switch for inverses. Another rule you need to know is called the horizontal line test. So the horizontal line test is for inverses. And in order for the inverse to be a function, it has to pass the horizontal line test. So it's in addition to the vertical line test, right? Vertical line test is for the original function. That's for the original relation. Horizontal line test is for the inverse. And again, if it passes for the original,
then the original is a function. If horizontal line just passes for the inverse, then, or sorry, the horizontal line just passes for the original function, then the inverse is a function. Give you a good example again. Y equals x squared, right? So I do y equals x squared. Does that pass the vertical line test? Yes. So the original relationship is a function, but would the inverse be a function? Because it fails the horizontal line test. But you apply it, and it's confusing. You apply it to the original function. If the horizontal line test fails for original functions, the inverse won't be a function. But if it passes, then the inverse would be. Like, for example, if I do a sideways parabola, so that relationship clearly fails for the original, but for the inverse it would pass. Now, one-to-one functions. This is might be a new thing. I don't know if you guys talked about it last year. One-to-one means it passes both vertical and horizontal. So example one-to-one would be y equals sine x. No, I lied. That would not be. That's not one-to-one. Y equals x cubed, or y equals x, sure. But sine would not be. Like y equals sine x, because you see how that fails the horizontal line test? That would not be. That would not be one-to-one. Or y equals x squared. So if f is a one-to-one function with domain D and range R, then the inverse of the function. And how do you guys write the inverse? Do you guys remember how to do that?
-1.
Good. Yep. It's not just, it's not 1 over f. Just so you know, it's not 1 over f. It's just a notation thing. Then whatever point you have on the original function, if a comma b is on f, then b comma a is on the inverse.
Oh, like that point's on.
Right. So whatever point is on the original, swapping the coordinates would be on the inverse. And that's actually really important because a lot of students there is one calculus principle which you guys won't learn until a year from now that a lot of students confuse because they just forget the fact that this is true, right? If 1 comma 2 is on my original, guess what? 2 comma 1 is on the inverse, right? Like, let's look at y equals x squared again. Y equals x squared. So give me a point that's on y equals x squared, any point. I like it, 2, 4. So 4, 2 would be on the inverse, right? Yeah, if you have x equals y squared, 4 comma 2 is totally on the inverse. So again, very simple concept, but just some people forget that from time to time. And when we have if or only if, that means it goes both ways. You can reverse the order of that. Like if b comma a is on the inverse, then a comma b is on f as well. So you can change the conditional and the conclusion. So or the hypothesis and the conclusion. All right. We're okay so far? All right. I know a lot of information. Let's keep moving. All right. So graphical interpretation. It's always symmetric. Always, always, always symmetric about y equals x. Very important. What that means is that if I took, let's say I took your knives and cut out a square piece of paper, and if I folded a square piece along that line, what's going to happen to two graphs? They map onto each other. Yeah, it's going to map onto each other, right? That's all it means. As it should, because you switch x and y. And also another thing you need to know regarding composite functions, is that f of g of x will equal x, and g of, let me type that up. That'll be a little better. F of g of x equals x, and g of f of x equals x. So that's always true. Actually, let me adjust that just a tad. There we go. So that's always a true statement. Did you guys learn about that too? Yeah, okay, solid review, good, okay. And true for every x in the domain of G and for every x in the domain of F. Okay. Let's keep on moving. So I'm just going to kind of read this little blurb here. It's nice to know that if a function is one-to-one, its inverse will be a function. That's fine. So yeah, because one-to-one, what that means is that it's passable with horizontal and vertical line tests, right? So the inverse will also be a function. However, in many cases, you'll have a function inverse is not a function, like y equals x squared. We know that. So to get a function that's not one-to-one, to have an inverse that's going to be a function, you have to restrict the domain. So let's back up a little bit here. Y equals x squared is this, right? Pretty clear its domain is all real numbers. But there's a problem. It has a mirror image, right? So we need to restrict something. What if I change my domain, but only have the right half? So I erase all this and keep this. So this is still y equals x squared, with the caveat that x is greater than or equal to 0. Now, does this pass the horizontal line test? Yes. You force the issue, right? So therefore, its inverse will also be a function, but there'll be a restriction that you have to show it that as well. So in this case, we restrict from x is greater than or equal to 0, the right side of the parabola. So the inverse, so when you solve this, right, when you switch x and y, and you square root, technically speaking, y equals plus or minus root x. However, if you have a restriction for this domain, right, what's going to be a restriction for this then? Positive x, but what are you going to say? What inequality would go with that? Yeah, because see how this is x? So then you have to switch. Everything switches. Not just these two. That letter switches also. So you can get rid of that positive and negative symbol and state that y must be greater than or equal to 0. So therefore, you're forced to keep the positive root x, not the negative root x. And it'll look like this. That's what you get. And if you were to graph, again, this one right here. So that's y equals x squared when x is greater than or equal to 0. That's y equals root x when y is greater than or equal to 0. And then if I drew this right here, I'm running out of colors. Here we go, dark blue. What am I drawing right now? Yeah, it's actually, I'm doing a terrible job of drawing it. So that was awful. I know I could do so much better than that. There is. Yeah, I could do much better. I'll just, here we go. Yeah, that looks like y equals x. Okay. So now let's do an example down below. Okay, example 9. You got root x plus 3. So let's do a little algebra here. So f of x is clearly this, right? Let's do the inverse. So initially I'm going to start with this, switch x and y. And what do I do after that?
Isolate y.
How do I do that?
Square.
Square both sides, great. Perfect. However, you're not going to graph x squared minus 3 in its entirety. You're not. Because what's the domain here for the original? What's the range for it? So guess what? You have your domain range for your equation, but we switch. We're going to switch. So for your inverse, your domain is going to be now 0 to infinity. And your range is going to be from -3 to infinity. So we're only going to graph the right half of that. So if you plug in 0, obviously I get -3. And I can only go greater than 0. So if I plug in 1, I get -2. Plug in 2, I get 1. So that's f. That's the inverse of f. And of course, root x plus 3, which I'll do in blue, starts at -3. If I plug in -2, I get 1. Plug in 1, I get 2. And of course, that's f of x. And of course, now I have no excuse. I have to be able to draw this crux. I have grids. Y equals x. Cuts that in half. And again, very important, you have to state the domain and range. You have to.
Because it was restricted for the original, it's better be restricted for this. And they swap.
So that should be pretty easy. So just to kind of put this thing to sleep, must state domain and range for inverse if such restrictions exist for the original relation. And hold on. Yeah. Inverse relation. Both domain and range. Yep. Okay, questions? We're good? Okay. Why don't you guys try number 10? I'll have you guys, my voice needs a little break. So why don't you guys try number 10? And we'll do transformations in just a little bit. We're doing great on timing. So try number 10. Give you guys a few minutes. We'll talk about it.
It's the cloud method.
Oh. Yeah. Let me do that for you guys. Okay, I'll do that. Well, it's basically a it's make a table. That's what it is. So so y equals x squared. Yeah, let me give you guys a little push.
Oh, and then you.
Exactly, right.
We did this.
I don't know.
Yeah.
We called it the cloud.
We did this. We didn't call it class.
Yeah. I don't know what we called it.
Obtain the This is class. just like the.
Okay, you guys should know how to get the new table after this.
And you guys would have. Obviously, you're adding 4x and adding 1.
Use the cloud method. Do you have to use the class method? Oh.
Day 2. Day 3. Oh, day 2 is it? Of course.
Sure, that's why I made squares.
I don't even know how
How are you doing the other notes then? Or just on paper?
yeah, I was.
Of course, we're good. Do you have your, do you need a homework copy too?
No, I'm not. I'll give you a mic. Yeah, let me go through this. This is smart. With the range of the function, and then you find the inverse. That you say. You don't have to draw the inverse function then.
I don't think I asked for it.
What is fine, this fine?
Just provide it. Yeah, you don't, actually, it wouldn't hurt to draw it. I mean, find it first, and then, yeah, so like switch X and Y and solve for Y.
We need to include the question.
But you're gonna discard it afterwards, right? Right, right.
It's supposed to be. What you said. I just realized you're supposed to find like the inverse of the Q function. What is the U for X squared? It's the surprise.
My brain just what happened? So like I just he did. I just misread it. So
Yeah, there's no name that's actually greater than. Why would it? No, it's the reach.
Okay, let me take a look. How you guys doing?
Yeah, I know.
Yeah, let me just do this really quickly.
Matthew is right. He was right.
Okay. So again, you should have your graph should look something like this: 4, 1. Plug in 6, you get 5. 5, you get 2. Technically speaking, it does look like this, but we're going to get rid of that part. If you do, so it's not 1-to-1, obviously. So the inverse won't be a function. When you restrict the domain, x is greater than or equal to 4. Range, y is greater than or equal to 1. We know that. And then when you find the inverse, your inverse should be this. Should be the positive square root, so root x minus 1 plus 4. So the endpoint's at 1, 4. And if you plug 2 in, you should get 5. If you plug 5 in, you should get 6. Solve the point switch. And there you go. And that domain is going to be x is greater than or equal to 1. And that range is y is greater than or equal to 4. So, okay, cool. We're okay with that? Okay, let's keep moving. Let's look at transformations, which we've already been kind of talking about anyway. Okay, so I'll read this little blurb here and we'll move on to the next page. Cloud method, blah, blah, blah. You guys know what that's all about. Now it's just really just switching x and y. I mean, changing x and y values, right? But that process is important. You have to know what you're doing to x and y so you can get the new points. So let's look at example 11 on the next page. All right. So, for example, if f of 3 equals 5, then I know 3, 5 is on the graph. And then generally speaking, a, b is also on the graph. So let's look at how these would be transformed. The first two should be pretty easy in the top two.
What does the plus 4 do on the outside? Yes, because that fixes a y coordinate, right? So naturally it would be increasing y by 4. And it goes up 4 also. This is always counterintuitive. And this always drives me nuts, but I have a way to help you make sense here. But the -4, First one's going X, so your impact is horizontally.
You think to go left forward, but you're actually going right forward. And here's how you can make peace with that. If you have y equals x squared, right? And then y equals x minus 4 squared. So 0, 0 is clearly a point on y equals x squared. So the output's 0, right? In order to guarantee the same output, what would your input have to be to guarantee the same output? That's why you go 4 right. To guarantee the same output as you would from the original, how would you adjust x? X would have to be increased by 4, not decreased by 4. I know we see minus 4, we want to go left 4. You don't. You have to add 4, go right 4, just so you know. So in this case, yeah, the first one's pretty easy. That's 3, 9, or a comma b plus 4. But for this one, that's going to be 7, 5, or a plus 4, b. And yeah, this also gets a little dicey with the we're doing the insides here. So you're clearly multiplying y by 2. So you're multiplying y by 2. Let me adjust my screen here. So if you're multiplying y by 2, then what's going to be the transform points here? Yep. And that's a stretch, by the way. That's totally a vertical stretch. Now, this next one's a little dicey, though. F of 3x. So you think to multiply x by 3, what are you actually doing? Yeah, actually dividing x by 3. And again, how do you make peace with that? If you have y equals, say, well, if use a square symbol. Let's do a radical, I guess. So you have root x, right? So I know 1, 1. If I want the same output, x has to be 1/4 now, right? To get 1 as an output still. So that's how you can make peace with that. So you got to divide by 3. So that's 1, 5, or a over 3, b. The next two should be pretty easy. You're changing y from positive to negative. So y changes sign. Here, x changes sign. And by the way, when y changes sign, what kind of reflection is that? About what axis? Yes, I know it's confusing, but it's reflection about the x-axis because it's a vertical flip. You're flipping things vertically. Y is positive, now it's negative. If you're flipping vertically, guess what? You're going over the x-axis, right? So that's to reflect, which we're going to talk about transformations on Friday anyway in more detail, how this relates graphically, but that reflects about the x-axis. This reflects about the y-axis because now you're doing a horizontal flip, right? You're going over the y-axis, you're switching the x-coordinates, you're going over the y-axis. But in this case, you have -3. Sorry, oops, I meant to say 3, -5. And of course, a, -b. And here I have -3, 5. And -a, b. Questions so far? We kind of did these piecemeal, like these said that, okay, we got like, going left to right, going up or down, vertically stretching, horizontally, shrinking, stretching, or dilations, we have reflections going on here. Now we're going to put it all together. This is where the fun begins. And the order matters. Gotta state the right order. Kind of like, I'm right now in baseball mode. I'm be in football mode in 2 weeks. But in baseball, there's like a lot of different pitches. You can see like the pitcher can throw you a four-seamer, could throw you a curveball, changeup, slider, sweeper, like all these different types of pitches. I kind of showed you all these different types of pitches, but then in the actual game, you don't know what you're getting, right? It depends on the game environment. So you have to be able to be ready for anything. So that's what's happening is these last two here. Like there's a lot of things coming your way. You got to figure out what's what, right? So you're going to want to do this first. You're going to want to do this second. You're going to want to do that third. It's all about PEMDAS. So what does that first thing do?
What was that first thing that plus 3? Slides left, yes, good.
So the first thing will be x minus 3. Or let me be a little more explicit. Subtract x by 3. Okay, what does that second thing do? That 2 there. So you're going to multiply y by 2. What does that third thing do? And you multiply, sorry, yeah, I meant to add. You add 1 to the new y. So yeah, obviously I have 0 now. If I multiply 5 by 2, then add 1, what do I get? 11, right? So generally speaking, it's going to be a minus 3, comma, 2b plus 1. Like that. And yes, shift 3 left, stretch vertical by a factor of 2, and shift. Let me write that out actually. And let's switch colors, go red. Shift 3 left, vertically stretch by a factor of 2, and shift 1 up. And it's got to be in that order. I am totally picky about this. I'm usually pretty lax about most things. This one, I'm incredibly picky. You got to get it right. Okay. So what happens next one here? It's a little tricky, this one. So technically speaking, you're actually going to, I know you guys are gonna think I'm crazy, but you actually are gonna do this thing first. You're gonna do this second, and this will come third. In a way, what's happening is it's almost like you could factor out the 2, but it's kind of weird because if you factor out the 2, then you have -1/2 on the inside. So I'm gonna kind of back up a little here. Let's say I were to do this. So what would that really be? That'd be f of 4 minus 1 minus 3, or f of 3 minus 3. Okay. Well, what is f of 3 here? 5. So you wind up getting 2 as the output. So the transformation is going to be 2 comma 2. That's why you take you add 1. Hold on. Now I'm kind of confused myself here. What was that? You add 1. I know but technically speaking, actually did subtract 1, right? Because I went from 3 to 2. But another way you can think about this too is oh, then you're right. We added 1 and then we divide by 2. Yes, you're correct. Yes. So first thing I did was actually shift 1 right. And the second thing I did was I horizontally shrunk by a factor of 2.
If we like pull the 2 out of the parentheses, was like after the 2 parentheses x plus 1 half, we want to do that.
Yeah, it's just it's a little tricky when you do it that way. Let's revisit that from later in the week. Yeah. the horizontally shrink by a factor of 1/2. Eddie, go ahead.
Then you divide first.
Well,
Then you divide.
Then you divide first.
yeah,
3 divided by 2 plus 1/2.
yeah,
So you just have to switch the order if you pull out.
yeah, that's true. Yeah, it's really mind bending. We'll come back to that. For now, let's just do it this way. Oh shoot, we didn't start. Okay, so we'll stop here. That's okay. Okay. So by the way, this right here, a plus 1. Thank you, Oliver. Appreciate it. Yeah, so that's that one. I think we're okay because we could wrap this up. So we'll say parametrics. I don't think there's any homework problems on parametric. Let me double check.
Usually it's 10 minutes. It's like my experience.
Yeah, we're okay, guys. We're good. Okay, yeah, because all right, so let's start the homework quiz.